Hi there, it's nice to have you back for our discussion of hash join in chapter 12 of the DB2 course. So what you might have observed in computer science in general is a sort of duality between sorting and hashing. Things that can be accomplished with sorting can also be alternatively accomplished or implemented or realized in terms of hashing. And it's no different with the database join algorithms. A merge join, of course, is the representative of the sorting-based camp. We require sort order in the inputs, we guarantee sort order in the outputs. The internals of the algorithms, they are based on the scan sorting, in-sync lockstep sorting of the join inputs. Everything screams sorting in merge join. It's different for hash join. This is the other side of the coin. All right, so hash join is also a specialist in evaluating equi-joins, which due to foreign key joins, for example, are probably the most prevalent kinds of joins that you will find in database workloads. All right, so it makes sense for join algorithms to focus on this particular use case. And indeed, hash joins can only be used to evaluate equi-joins. Okay. Of course, sorting plays no role in the evaluation of hash join. It's all about building hash tables. Indeed, the hash join algorithm proceeds in two phases, in the so-called build phase and in the probe phase. It's in the build phase when we are actually constructing a hash table, right? That constructed hash table is then later used in the probe phase to look up for join partners in a particularly efficient manner. Okay, so in the build phase, one of the input tables is red, and its rows are placed inside an hash table H here. Okay, of course, this will require memory to store the contents of the hash table. And of course, our desire would be to store the entire hash table H inside RAM. Well, if this is possible, that would be the best case, the ideal case for hash join. So given plenty of working memory, we find plenty of space to build our hash table H, and that would be the ideal working environment for our hash join algorithm. If the working memory is tight, then hash join might still apply, but as we will come back in, I think in the next video, this will force hash join to iterate these two phases, and well, the communication between the iterations involves some additional I/O and additional work, which will slow down the overall endeavor. So, well, indeed, we are aiming for a situation where the hash table that we are going to construct will fit into memory. As I told you, it's exactly one table that will place its rows inside this hash table. This one table is also called the build table. Okay, so in the nested loop join case, we had inner and outer tables. In the merge join case, we had left and right tables. Now in the hash join case, we are talking of build tables that we will use to populate the hash table H, and then about a probe table, the other table, whose rows we will read and then check against the rows that are being placed in the hash table for particular join partners. Since the rows of the build table have been distributed into the individual buckets of hash table H, we have the opportunity during probing to not compare the rows of the probe table against all the entries in the hash table, but only against those entries that have been placed in particular hash buckets. So a very tiny, hopefully very tiny fraction of the hash table H only. This is where the efficiency of the hash table of the hash join idea stems from. All right. Well, of course, we will look at the details in due course, but this is the basic idea. Build a hash table, then probe against that build hash table, but focus on very few, hopefully on only a single bucket inside that hash table, and focus on that bucket to find potential join partners. As I told you, if that hash table is too large for the available vacuum memory, well, hash table and the basic idea might still apply, but we would maybe need to iterate the building and probing here. And of course, that involves some temporary storage that has to be filled and then reread again. We will see the consequences of such iteration when we talk about the version of hash join that is equipped to do that, the so-called hybrid hash join. All right. If you look at the description of this build and probe phase here, there is no mention of input order of the participating relations. We will just read all the rows of the build table, place them into the hash table, then we'll read all the rows of the probe table in some order and probe against the rows that have been placed in particular buckets. We will not require input order, so that's fine. No constraints or restrictions there, but we will also not guarantee output order. Once we have performed the probing phase and we have indeed found our join partners, well, we will emit rows in some order, but we will not be able to guarantee a particular output order. So hash join plays less of a role in plans that are full of interesting orders that maybe downstream subsequent operations in the plan could benefit from. All right, so let's look at this sketch of an example of the hash join situation. It's again the situation in where we would like to join our one table against the many table, the join playground that we have used so many times. Of course, we are talking about equi-join operation. So the A columns in both participating tables make for the join condition that we will evaluate here. All right. Well, hash table construction won't be possible without a hashing function. So with each hash join implementation comes a hash function. All right, this is function h here, which we will apply, of course, to the values found in the join columns A. And this is the case for both participating tables. So for the build table, we will use the A values here to construct the hash table and place rows in particular buckets. In the probe phase, we will use the hash function on the other side of the join partner here. The A column of the probe table will be fed into the h function, into the hash function, to quickly identify the hash bucket in which we can find potential join partners. All right. But this is still a two-phase thing. So in the first phase, in the build phase, we would only look at the left-hand side of this particular picture. So let me draw a line here. Everything to the left of this line would be relevant in the build phase. All right, so let's assume that the one table is the build table in our setup. And there is, of course, good reasons for that. The one table, if you recall, in our playground has been the smaller table. I think it contained like 10,000 rows, while the probe table contained like 500,000 rows. So the one side of things is smaller. Since the one side will be placed inside the hash table H here, all right, it of course makes sense to pick the smaller table as the build table. This will hopefully lead to smaller hash table sizes, and working memory is precious and probably tight. Okay, so we will scan the entire build table, table 1 here, and each row will be fed through the hash function h here. Indeed, the a value. This a value will be placed into the argument of our hash function. The result of the hash function, the hash key that will be computed, these are the hash keys, will determine where that particular row 01, for example, will be placed inside our hash table. You can see that the hash function maps the key value 1 to key k1 because we find the row 01 here in the hash bucket that is associated with key K1. All right, and this is how we fill our hashing table, right? So O2 has a key value of 2, all right, and we can see that the hash function maps the key value of 2 to this bucket with hash key K4. This is where we find the particular entry. You see that we find the row placed there. We will also have an indication, explicit indication here, that the key value that has been used to place it here has been the value A equals 2. All right. So all of the rows of the build side are placed inside the hash table H here. Of course, there might be many rows in one particular bucket. So there's, in this tiny example, there are already 2 rows placed in the hash bucket with key value K1. All right, so now the build phase has finished and we do not require the build table, table 1 anymore. All right, so what's happening now is the probe phase, and we would redraw that separation, that board. Oh no, let me redraw it this way. So now everything to the right-hand side of this dividing line will be relevant in the probe phase. In the probe phase, we will scan the probe input, and we will scan it only once. Okay, if we read the row M1 here, then of course we will use its A value, place it inside the same hash function H, and this hash function will distribute the row, or will route that particular row M1 to, well, based on the value 2 here, it will route it to this hash bucket in which we have already placed row O2. Okay, so the key value, hash key value K4 is the same for rows O2 and for rows M1. All right, so potential join partners for M1 have to be located inside this particular bucket. All right, so I will check all of the entries in this particular hash bucket if they indeed agree regarding their key values with the key value of the current row. If this is the case, then one join partner has been found, and we can generate this join pair here. Okay, and this is repeated for all the rows of the many side, of the probe side actually. So let's look at row M2 here. Its key value is A equals 3. Mapping that using the hash function will lead us to the hash bucket with key value K1. That bucket hosts 2 entries here, all right? So we will only check this one particular bucket, not the rest of the entire hash table H. Only this particular bucket will be checked whether we can find a join partner for row M2. This, of course, will require a comparison of the key values of row M2, which is A equals 3, with the key values that have already been placed in the bucket. And we find a match here. So M2 can be joined up with O3, and this is indeed found in the output. All right, so only with those rows placed in the associated bucket, we really have to perform the key comparison here. Okay, all other rows in all other buckets below here are of no relevance when we are looking at this particular row. Okay, and all of this is of course repeated for the many rows, and this will lead to the entire join result, which we can write here as indicated in the picture below. So that would be the basic idea of hash join. Of course, its efficiency derives from the fact that once we are in the probe phase, we only have to check one particular bucket for potential join partners, and only in those buckets we would actually perform the key comparisons. All right. The pseudocode that would be associated with this algorithm is the hash join function or routine that we have shown here on slide 23. Well, its API looks almost the same as for merge join. of course, there will be the two participating tables, and they are not called left and right here for good reason. They are build and probe now. Okay, so CL shall be associated with the build side. CR shall be the column associated with the probe side. Again, there is no need to communicate the comparison relationship between CL and CR. It's apparent that the comparison predicate between CL and CR must be equality. We are only talking equijoins here. The structure of this algorithm should be familiar by now. Of course, we will generate a join result J and initialize it here at the beginning of the routine. At the end of the routine, it's exactly J that will be returned. We also prepare an empty hash table at this particular point. So H will be our hash table. At the beginning of the algorithm, it will be empty. This will change in the build phase when we iterate over all the rows of our build input and then place that entire row into the hash table in the correct bucket. Which bucket that would be? Well, we would apply the hash function to the join column of our just read row and would thus identify the hash bucket. Okay, so the hash bucket might already carry some rows. It will now carry one more row, the B row that we have just placed there. And this is performed in its entirety until we can build the entire hash table. All of this under the assumption that hash table H will fit into working memory. Should working memory not suffice, we will have to switch to hybrid hash join. This is discussed in the upcoming video. All right, so build phase done. Now it's phase 2, the probe phase. Now we will iterate over the probe input, the probe relation. And all of the rows that we read there will be called P. Now we will check the hash bucket, the one particular hash bucket inside our hash table that might contain the potential join partners. How do we identify this hash bucket? Well, we will apply the same hash function H here, but of course apply it to, well, the right hand side column CR here, the join column that is associated with the probe input. All right, so this identifies the bucket of potential join partners. Inside that bucket, and we may find some rows that have been placed there because their hash key is the same, although their join column value, the CL value that we used, is different from the CR value we are currently looking at. That's why we need to reevaluate this join predicate while we scan the potential join partners in the buckets. But only for those potential join partners, we have to evaluate this comparison. Once we find potential join partners, then it's time to append them to our join result J here. And that's the simple logic behind hash join. All right. In a real plan, in an explain plan of PostgreSQL that contains such a hash join, you will find this typical pattern. Okay, so an explain on a hash join based plan will always show this pattern. It will of course show the hash join algorithm, and below that hash join algorithm there will be two inputs. Of course, hash join is a binary operation, so that would be one input, that would be the other input. And as this hash already indicates, you probably have guessed already that this second input, the lower input in the explain output, is indeed the build input, right? Because well, it carries this hash operator here, which represents the construction of the hash table. All right, so everything below this hash node would be, well, considered the build side of things. It would be a subplan, maybe it's only a sequential scan of the build table. All right, there's no iteration going on, as which is different, for example, to the nested loop join case. We scan the build table once and we place its row inside the hash table, which is constructed in this hash plan operator. Perfect. Okay, The other side of the input, of course, is the probe input. And indeed, it also scanned once. We scan the probe input once, apply the hash function, perform the comparisons in the appropriate hash buckets, and then, well, the comparisons is actually which comparison is being performed is annotated here in the hash condition annotation in the plan, and then construct the final result. Okay, what you will also see, and I think we can switch over to the terminal in a minute, what you will see, and we have already said this, well, you will find that the system typically decides to use the smaller table as the build side of things because it will lead to smaller hash tables. Working memory may be tight. Okay, and what you will also notice is, although there might be indices defined on the join columns, on the column A, for example, of the many and one tables in our playground, you will see that these indices go unused when hash join is being performed. We have to read all the build rows and all the probe rows anyway. We don't require them to arrive in one particular order. There is no benefit to be had of using index scans here. Of course, we could use index scans to apply or evaluate local predicates that only involve the probe and build inputs. But regarding the hash condition, the presence of indices make no difference here. All right, so let's quickly play with this on the PostgreSQL terminal side of things. Let's quickly recall our one and many input tables. The one table with ABC columns with an index, but hey, index, I don't care in the upcoming discussion, and the many table. There it is, ABC columns. This is the larger table. Okay, so now let's perform an equi-join between the one and many tables, and yep, is the equi-join condition. This is an indication that indeed that hash join is one implementation alternative for this particular plan. Let's see what happens. All right, so indeed, a hash join has been employed. Just as we hoped here. All right, okay, the hash condition, the condition that then has to be checked in the appropriate hash buckets is this condition. Of course, what else could it be? Right, and then there is, of course, the build and probe inputs. Let's look at the build input first, which can be identified by looking for this hash entry. It's the lower entry normally in the output, explain output of PostgreSQL. So we see that indeed the hash table is built by scanning the rows of the one table. And indeed, the one table is the smaller table. We had expected that, actually. Well, all of these rows are being read. A hash table is being constructed, and you can see that that hash table will have 2 to the power 16 or 16,384 hash buckets. All right. We could perform all of this in one go, so no need for iteration, no need for the hybrid hash join technique that I've already hinted at and that we will discuss in the upcoming video. And indeed, a hash table of 714 kilobytes was sufficient to build the hash table on this one table. You see that well, the rows that have been placed inside the hash table are indeed full one rows with the A, B, and C columns present. Why? Well, because in the output later on we will need all of the one tables here, and well, that's why they are also placed in the hash bucket. Of course, they occupy some space there, adding up to 714 kilobytes. Right, the loops indicator reads 1 here, no iteration is going on. This is not just not like in the nested loop case. We scan the relation 1 once and place its row in the hash table. And of course, it's the same for the probe side of things. There is a loops of 1 here, and well, nothing much to say here. Only to underline that we indeed are using sequential scan here and no index scan whatsoever. Right. So let's let's modify this query a tiny bit and indeed remove the requirement that all the O columns, the A, B, C columns of the one table have to occur in the result. Okay, so that would be a simpler query. It would indeed be a so-called semi-join. So we are looking for all rows on the many side that indeed have a join partner on the one side. We are actually not interested in the one data itself. This is a semi-join. Well, what we would hope to see here is that the hash join and the hash table construction does not bother to actually copy the B and C columns of the one table into the hash bucket. They will not be needed later on, and they would only occupy space and help to let the hash table grow. We would rather like to avoid that. So let's see how PostgreSQL copes with that. Okay, so this is the same plan as we have seen before. It's almost the same plan. Hash join has been employed. All right, again, the probe input is the many side, the build input is the smaller one side. You see that sequential scan already only delivers the A column here. The B and C columns are being omitted. Okay, also in the hash table, we will construct hash bucket entries that only carry the A value, the key value, to be compared later on. And as you can see, indeed, the memory usage has gone down. It went down from 714 kilobytes to only 480 kilobytes in this particular case. All right, perfect. Okay, so now one more thing. Let's reduce the available working memory size. It has been 4 megabytes, the default up to this point, but we will reduce it to 64 kilobytes temporarily at least. All right, this should be a challenge for hash join because as you see here, even for the semi-join case, which we will now repeat here, even for the semi-join case, well, the hash table size exceeded 64 kilobytes. All right. And I think what we will now see is that hash join will turn to an iterated behavior in where more than one batch, as it's called, more than one batch will be produced. And this is already a hint at our discussion of the upcoming video. So memory has already been reduced. Okay, so let's perform the hash semi-join again. All right, took a bit longer here, and indeed, this is the same plan. One is still the build input, but well, we only found space for 2048 buckets now. All right, so this is all we can fit into a hash table of 36 kilobytes. So indeed, we are respecting the working memory size of 64 kilobytes that we have defined here, which of course is ridiculously low. Okay, so 36 kilobytes, this led the system to an iterated behavior. So this the building and probing will be iterated, and we will look at the details in the upcoming video. Indeed, only one of the batches fits into memory, and all the other 15 batches had to be written to temporary disk storage. Okay, right. So of course this is leads to more I/O operations and an overall execution time that increases. All right, I think so. Let's quickly switch back to 4 megabytes here. Right, I think that should conclude our introduction to hash join. So as we've already seen here, this iterated behavior, the hybrid hash join, really is crucial in situations where working memory is tight or where probably the participating inputs are super large. This is stuff for the next video. I hope to see you around and that you stick around. See you then. Bye-bye.